In the first proof in 6, what we did is we found that if we had a four-sided figure and if the diagonal created two congruent triangles, then that four-sided figure or the quadrilateral would have to be a parallelogram. So we have a sufficient condition to prove that a four-sided figure would be a parallelogram, and that is draw the diagonal. If the diagonal creates two congruent triangles, then it would force it to be a parallelogram. In this condition, in part B that we're looking at, it says, what if we have a four-sided figure and it has two pairs of opposite angles that are congruent? Then, is it a parallelogram? Does it force it to be a parallelogram is the idea behind this. So we're going to start off with this four-sided figure. We're going to mark in it kind of what we already know is to be given to be true, that the opposite angles here and here, and here and here, are congruent. So what if those angles are congruent? Does it mean that this has to be a parallelogram? Pardon the interruption, I got to grab the door here. Sorry about that, but I got that taken care of. So this proof is a little bit different than the others that we have, and every once in a while you run into one or encounter one that's a little bit unique and different. So let me start off by getting back to another part of this picture. If I throw in a diagonal, what we know for sure is that these three angles, 1, 2, and 3, have to add up to 180 degrees. So basically, in this triangle, we have 180 degrees of angle measured. Then, in this triangle on the top, we'd have exactly the same analogy that these three angles in green would have to add up to 180. Now this kind of comes back to a point or a fact that we can say that in any quadrilateral, in any four-sided figure, there are a total of 180 plus 180 or 360 degrees, oops, 360 and then a degree sign, of angle measured. So anytime you have a four-sided figure, it's always going to add up to 360, and we use the analogy of divided into two triangles, and then we have 180 plus 180, 360. So now I'm going to remove that and come back to the fact that we knew that the opposite angles were congruent, so these are the pairs of angles that have to be congruent. So if we were to take all four of these angles, A, B, C, D, add them up, they would have to equal 360 degrees. And I'm going to start writing out this proof so that you can kind of see where it's headed. So first of all, we're starting off with ABCD is a quadrilateral. That's given to us. And we're also given that angle A is congruent to angle C, and angle D is congruent to angle B. And this is all by given. Now we're going to use the fact that we know that we can take the angle A plus the angle B, plus the angle C, plus the angle D, and they will always add up to 360 degrees because the sum of the interior angles of a quadrilateral is 360, the point that I just kind of made prior to this. So the sum of the angles of a quadrilateral is always 360 degrees. Now we're going to use some substitutions. I know that B and D are the same, so what I'm going to do is I'm going to replace all of the, I'm going to do it this way, I'm going to leave the A's and B's in there, I'm going to take out the C's and D's, so angle A plus angle B plus, now angle C is going to come out, and I'm going to replace it with what angle C is equal to, so A is going to go in for C, so plus angle A. I'm also going to do the same thing with the angle D. I can get rid of the D and replace it with angle B. So B is going in place of angle D. So plus angle B. And this is by a substitution property of equality. And then we're going to do a little combine of like terms. I have an angle A there and angle A there, so that's two of those angle A's. Plus the same thing with the angle B's. I have two of those that add up to, I forgot my 360 here, 360 degrees. And that is by collecting like terms. Then we're going to use a division property of equality. What I'm going to do is divide this entire equation by 2. So if I divide everything by 2, we're going to have an angle A plus an angle B equals 180 degrees. And that is by our division property of equality. Now we've made the statement that A and B have to add up to 180. But if A and B add up to 180, here's our A and here's our B. If they add up to 180, that means they are the same side interior angles on these two lines, AD and BC. And if same side interior angles are supplementary, it forces the sides to be parallel. So now I know that side AD is parallel to side BC by the same side interior angle theorem. So we've proven that side. Clean up this picture a little bit. We have now proven that this side AD is parallel to BC, and we're still maintaining what we know the facts that these angles are congruent. Well, we also need to prove that the other sides, DC, so somehow I got to get side DC parallel to AB. And that means we want to look at another pair of alternate or same side interior angles. So what I want to do is prove that angle A and D have to add up to 180. Well, if we know already that A and B add up to 180, we knew from a fact earlier that angle D was the same as angle B, so I'm going to replace angle B right here with angle D equals 180, and that is by substitution once again. Property of equality. Well, if A and D add up to 180, A and D by their location are same side interior angles, and it forces those two lines, DC and AB, to be parallel. So AB has to be parallel to CD by the same side interior angle theorem. So therefore, what we've created is the fact that both pair of opposite sides are parallel. So now we know that figure A, B, C, D is a parallelogram by definition of a parallelogram. So this is another sufficient condition to have us prove that if it's a four-sided figure that has opposite angles that are congruent, then it must be a parallelogram.